saltiest.
I don't know what you're talking about. I have no idea what you're talking about.
You just can't take it.
Yeah, I can. Good morning, everybody. Welcome to Advanced Refrigeration Podcast. Here with hosts Brett Wetzel and Kevin Compass. How was your New Year's? You look spry. I guess no drinking last night.
No, we just went out to eat and then drove back in a blizzard.
Oh, it's snowing up there?
By me it was.
Oh,
Where
yeah.
we were eating, it wasn't. It was. I got halfway home and it just turned into a whiteout from lake effect snow. So they got like 3.5 inches in an hour. So it was just a trip.
Yeah.
So then I'm headed back to Detroit today.
Wait, today you're going to Detroit?
Yeah, so that way I'm down there and I could start early in the morning.
Oh, okay. I thought you were actually physically working today. I guess you are because you're driving, but I thought for some odd reason, I thought you were like going down there after this and working.
No, I'm going to drive down. That way I'm already down there and I don't have to deal with a 4.5 hour drive in the morning.
Yeah, I get it. You like getting ready first thing in the morning, and then you're spry and not irritated. Or is
that, and I just don't want to deal with the stupid highway BS in the morning, because I guarantee if all this melts and it is just going to turn to an ice skating rink.
Yeah, I get it. I get it. I've been closely paying attention to what it's going to be when I go up to Montreal. Currently, it's going to have a low of 10, so I'm have to dig out my actual winter jacket that's probably in my truck for going into freezers, because I wear sweatshirts all winter long here.
Yeah.
Yeah.
I would not go to Montreal.
Yeah, when I was talking to Andre, he's like, "Hey, would you want to come up here?" I was like, "Preferably not in January, but if I have to."
Preferably not in January.
Because it's cold, man. Like usually when you go on like a vacation, right? I'm like, not this is a vacation, but when you're trying to get away somewhere, you go somewhere warmer typically. I think right now it's like 35 degrees here in sunny Dallas, Texas, and it'll be at least 50 by noon.
I hate you.
January. Yeah. No snow. Not even a drip of snow this year, which is awesome.
Yeah, we've been lucky besides yesterday, and it was a icy show, so
I'm sorry, I'm still dying. Yeah, I can't get rid of this cough at all.
Between that and then the massive eye infection I got, yeah, that's the double whammy.
I told you what that was from. You can't do that shit more.
It has nothing to do with that. It was all from getting my eyes and then having an allergic reaction to whatever they gave me for my eye. Then it made it 10 times worse. I should have never even went to the doctor.
Are you allergic to any kind of antibiotics?
Apparently, whatever they gave me.
No, I just didn't know. Like my wife, she's allergic to, so she can't take that when she gets sick. So I just didn't know if there was a specific antibiotic that you were.
Whatever that was, yeah. Like my eye hurt 3 times worse than when I got shit at work.
That's crazy. I guess today, since we talked about hot gas defrost and the operation, today we'll talk about diagnosing hot gas issues with CO2. How about that?
Sounds good.
Yeah, let's go.
So,
anything you want me to bring up, or what do you want me to do?
Let's start with the low temp style with just using the low temp defrost pumps. So guys, on this particular style, like we said in the beginning, this is using the low temp discharge of the low temp side of the booster rack to do your hot gas defrost. So all of your heat is coming off of the low temp compressors. Whatever discharge superheat they have is what's going out to your systems. Now, a couple things. So we have to have some sort of differential here. So you have that defrost differential valve that we talked about on the line leaving the oil separator. So you have a valve setting your minimum pressure on the compressors. So in this instance, they're shooting for like 500 to 514 PSI pressure difference or pressure on the compressor side. So your compressor outlet, the oil separator outlet, they're shooting for a 500 to a 515 PSI pressure on there. Now, what they're doing is utilizing that pressure to be your defrost pressure. And then everything on the other side of that valve is going to be lower. It's going to be at your medium temp suction pressure, because remember that discharge of those low temp pumps is eventually dumping into the medium temp suction, whether it be through the accumulator or the intercooler. It's still going to the medium temp suction. So that is going to be medium temp suction pressure. So that, go ahead.
Sorry, no, all I wanted to add in here, so it doesn't show it on this print, but I'd assume that we'd probably have a oil separator here, right? Because typically the compressors of the low temp are typically going into the medium temp compressor suction, but in this case, it's actually going to the intercooler. So if we don't separate the oil before it goes into the intercooler, you're essentially going to lose all that oil that you are pumping through those compressors out into the intercooler. So theoretically, if you remember how Kevin said last podcast that maintaining the intercooler there is to maintain a liquid level for our medium temp circuits as well as our low temp circuits. So that being said, if that's going to have liquid in there all the time, that means the oil is going to sit on top of that liquid and never going to get back to the pumps. So even though this print here does not show an oil separator, this rack will have an oil separator. So if you were have a coalescing filter oil failure on your oil separator, you might lose all that oil and it might be sitting in your intercooler.
Correct. And this style setup, like a lot of the hill boosters, you don't see two separators. They generally just have one separator on the transcritical compressors, because most of your oil makes its way back to the low temp and gets pumped into the medium temp suction. They're also not utilizing a massive intercooler or a massive accumulator. They're taking that and just dumping it right into the suction, or they're going into a small, maybe like 20-pound accumulator. So they don't have the problem that you run into with this larger system. If you're going to run hot gas on the off the low temp pumps, you're going to need that separator, or else you're going to throw all that oil from those compressors into the evaporators when you go to do the hot gas. So with that being said, so on here you have your low temp compressors down at the bottom, and you're going to feed up, and then you have a line, the red line coming up, and that's going to feed your hot gas supply, and you get your valve there. Now, if that inlet pressure to that valve is dipping down to medium temp suction, you're not going to have any hot gas flow, because you're going to get a tiny bit of flow, just whatever the pressure difference is. But if you don't have enough pressure flow, differential flow from the discharge of the compressors back to the medium temp accumulator / intercooler, you're not going to get proper flow on those coils. And generally, if you're doing reverse defrost, it seems to be like 50, 60 pounds is what you need differential to get proper flow through these coils.
I said that makes sense. The oil differential, right? In HFCs or HFOs, we only have to have like 30-pound differential. We're in CO2, we need about 75. So it makes kind of sense why we need more of a differential in CO2 as far as the defrost differential than we do with hydrocarbon or hydrofluorocarbons or hydrofluor, or I can't ever say that word right. The HFOs, where you only need 20 pounds, where this, you're still needing that 50-pound differential, a little bit higher than what you would.
Correct. And the other thing to keep an eye on, guys, is when you're going through and doing these, is making sure that your discharge temps are high enough. Now, if you're going to defrost and you have coils floating back, if you have low superheat, the low temp compressors, you got to remember all your heat is coming off of those. So if you don't have the heat for compression and the heat of added compression, you're not going to get a good adequate defrost. It's going to be worse than a cool gas defrost with low head pressure. It's just going to be a really long, drawn out process. That's why, like me and Brett were talking on the last podcast about boosting or changing set points. And to me, that's the best way to accomplish this in an energy efficient way, is to run a superheat set point of 6 to 8 when you're going through in the normal refrigeration, and boost it up to 10 to 12 when we're in defrost, so we get a little bit more heat out of that side of the compressors.
How much you want to bet that the next couple of weeks you start seeing that come out? Because that's a really good idea. inherently, you're only running at, you figured it out, it was like 42 degrees saturated coming off, boosting off of this, right? Like for where it's taking the hot gas from, what it's trying to do, what would you say, 550 pounds is what it's trying to maintain, right?
Roughly about that. I mean, it kind of floats in there because it's a mechanical valve. So it's got some
It is.
Yeah, it's a mechanical Danfoss valve.
What? Ooh, okay. All right. Now I'm curious about what is the model number of that?
I don't, but it's the one you've shown in like million slides. It's that same style valve they use in all the industrial style stuff where you could build it up to like different modules.
Oh, gotcha. All right, I have one of those. Hold on.
So it's the same style valve. It's just a pilot operated valve, but it's designed for higher pressures.
Gotcha.
So it's a pilot operated valve. You go through and it's no different than setting a normal defrost differential valve. The more you go in, the more differential the higher the inlet pressure is going to be. It's like, don't think of it like a differential valve. Think of it like a holdback valve. So it's an inlet pressure regulator in this sense.
Yeah, because you're essentially, your differential is going to be made up by whatever your flash tank pressure is, or I'm sorry, whatever the intercooler pressure is going to be. So theoretically, that's going to be whatever your medium temp suction is versus whatever that pressure is. So it would be actually an inlet pressure regulator because it's trying to maintain X pressure right there, correct?
Correct. And now one thing to keep in mind is if you're floating the suction pressures on these racks, make sure that if you float the transcritical side compressors, if you float that, make sure you still have enough differential.
Gotcha.
Or else you may need to drop the float pressure while you're defrosting. So to have enough pressure differential, the two set points is, I think, is the best way to do this for the superheats. Is that way you get a little bit more heat out of it. The only problem is I think only a few EMS controllers have the ability to run dual set points for like everything. I know in like microthermal you could change the dual temp on a case controller, and you could change everything. Every setting has a dual temp application, whatever, for your fan start, from your superheat to your coil outlet temp stuff. Everything has a dual temp set point. With that's where it would be king. I'm sure the CC200 probably has something in that application too.
Does the XM? Because I don't has what's that?
No, it doesn't have you can't change like a secondary superheat.
Oh, so you'd have
offset maybe.
Yeah, you either have to do an offset or have that input, like whatever, change that setting into an input and then have an enable that essentially, like whenever these cases go into defrost, it essentially changes the enable, which will give it a higher superheat set point, right?
Yeah, and starve the coils a little bit and then make your heat. So that's one thing with this style system, guys. And then other than that is making sure your EEVs. So if you are doing inverse style hot gas defrost down the liquid line and through the EEV, making sure that EEV is opening up all the way and making sure that you actually have the correct size EEV. With the Carnot systems, you need to be running a minimum of an SCR-C. So you have to be running a minimum of that. No valve smaller than that, or else they won't have enough flow through the port. No Bs, no As, no double As. Doesn't matter what it's on. Even if it's on a small coil, it has to be an SCR-C minimum. You're muted.
Ah, damn it. And that's just so you can get the flow when you actually go into defrost, because otherwise you wouldn't have the proper amount of flow. Is this the type of valve that you were talking about?
Yeah, it's missing like half of it though.
Yeah, well, this is the one's going to be for this. This is going to be a regulator. This is going to be full open or close. I mean, this one, these valves basically do whatever whatever is on here. So this is yellow. It might be a hand expansion valve. I'm not really sure. Does your valve have an IMTCS on there?
No, it's just a manually operated.
Okay.
So,
all right, so it's just a pressure regulator then. Okay, because I know you can take a lot of those valves and put that head on there and have it a mag-driven valve for pressure or whatever it's trying to do.
Yeah, no, in this situation, it's just a simple mechanical valve, which I think is the best application for this because it's nothing, no hunting really, and maybe a few PSI here and there. It's mechanically set. It just holds its setting. But if that valve isn't functional, you have no defrost.
Gotcha.
So the other thing is, guys, making sure that you have the proper size EEV. And we've had some issues here as of lately with distributors getting put in on these inverse flow systems, and we're not flowing enough backwards through the distributor orifices and distributor lines. So we've had some coils where they don't get all the way to the top, that doesn't get defrosted, or the bottom doesn't get all the way defrosted. And it's become an issue with the manufacturing of not getting enough flow through the distributor orifice, just like we have with generalized refrigeration. The orifice needs to get moved, and they almost need to run the check valves around it. But in this situation, what they're having to do is they're having to change the distributor orifices and lines. They're having to upsize them so that we can get enough flow in defrost through them. Like if you were measuring them, we were taking and measuring them with temp probes. And by the time we were getting to the actual coil through the drain pan, because it goes through the pan first, the liquid line goes through the pan, comes out, goes through the valve. And then by the time we were getting to the distributor orifice, we were below freezing.
So it's the equivalent of not having almost like a hot gas solenoid feeding it, because you're not giving enough flow. But in this instance, it's just really expansion valve that's kind of the deciding factor on how much flow it actually gets.
Correct. And then the way you do this, you could also use the expansion valve to throttle defrost.
You could
use it. Say if you had one coil that was defrosting too much and one coil that wasn't defrosting enough, if you were running multiples, you could shut the EEVs a little more, and you could force more hot gas through one side than the other. And
that would get a little complicated.
It would get a little
complicated. Lot of programming.
Not if the case controller's doing it. If the case controller's utilizing it, if it's already maintaining that, if it's maintained, it would be fairly simple, I bet, for them to do that.
But still, if there's a nozzle in there, you're kind of screwed, and
yes.
You still have to, yeah.
Unless there's a nozzle, you're screwed, and they're going to have to. They're coming up with different ways to do it, and there's no real way to bypass the nozzle in the inverse way using the valve, because
check valve is going to be the only way. Check valve
because you're going the same way in normal flow refrigeration, because you're going down the liquid line.
Yeah.
So there's no way to do it besides solenoids. And
check valve and solenoid, right?
But at that point, you've overcomplicated and made it more expensive. So there's no reason to go inverse anymore. It's just forward flow or non-forward flow down the suction is the way to go at that point. And now, if you look at this same scenario, you could do down the suction and back the liquid. It wouldn't be that big of an issue. You could do the same thing instead of feeding into the liquid line on these. You could feed down the suction. You would shut your EEV at that point, and you would feed down your suction line, and you would bypass your expansion valve with a check valve, and you would come back down the liquid line with the hot gas after it's been condensed into a liquid. And in this instance, you're going to dump into the intercooler, which is the medium temp accumulator. So you would dump back into there, and that liquid would get circulated back to the system. You could also dump into the flash tank if you raise the pressure up high enough on those compressors.
Yeah. Also, another thing that could potentially happen is if you have not enough capacity on you're running summertime, right? And if you don't have enough capacity because you have a compressor that's not really cooperating all that much, you could potentially have a higher elevated suction pressure, and then in turn not have enough capacity to bring the pressure down to set point, and then essentially wouldn't have your differential. So you could have a differential flow issue because of your medium temp compressors, right? Makes sense.
Yeah, no, you would be handicapped by that differential. So the lower the differential, the lower the flow through the coils. So
have you ever seen that happen?
Not too much, because most of these racks have enough capacity that they're fine. Yeah. And most of the racks where I see not gas utilized, they're utilizing the low temp only for the low temp. They have a booster rack for the low temp, and that is it. And their medium temps are on straight transcritic, or they're on straight medium temp racks. They don't have they aren't using the booster side of the transcritical rack to do the medium temp. They have separate standalone medium temp racks for that. Which I'm not the biggest fan of 4 racks in this situation. I'd rather have just 2 bigger racks.
Yeah.
I think they run a lot better.
So on the rack that you had, does it actually have the parallel compression?
No parallel compression.
So instead of you having this right here, then essentially this line would just go right over here as a BGV instead of the actual parallel compressors. Yes.
I don't even, yes, correct.
Yeah, you'd get rid of these compressors right here, the parallels, right? And then that line would go directly into the suction line here. And then, or does it go to the intercooler?
It goes the hot gas dump line you talk about?
No, I'm talking about like, because this diagram here has parallel compressors operating the flash tank.
Yep.
So all you have is just these parallel compressors knocked out, and then this line would go over to the suction of the medium temp transcritical compressors with a BGV in the middle.
Yep.
Gotcha. Cool.
I've only seen one rack with we only run one rack with parallel compression. It's just not, I don't know. For everything I've read and everything I see, it's just not worth the payback. Most of the time, they end up sitting most of the year and either logging full of liquid or breaking or getting turned into additional capacity for the medium temp.
Yeah. So if anyone doesn't know what we're talking about, you usually have your medium temp suction running at, I don't know, in this case, it's 420, can be as low as 18 degrees saturated, maybe even lower in some instances. But then you have your flash tank, which in this instance is at 603. Usually what I've seen is 490, 510, somewhere in that wheelhouse. So you have a fairly almost 100-pound differential of distance there. That essentially means that it's sucking out. It doesn't have to keep the pressure down that low. So theoretically, what you could do is just run a separate suction just to maintain the flash tank. And then instead of you'd actually have a BGV also there just in case something happens with those parallel compressors. Because then you're not having to use the suction going all the way down to plus 18 to maintain a plus 46 or plus 38 saturated suction for your flash tank. So that's essentially all it's doing. Kaiser Warren uses this on their ETE or their XTE. The Danfoss trainer actually has parallel compression on there too, as well, working alone, but also can work in conjunction with the ejector system. Go ahead.
Yeah, it's just, it ends up complicating it. And yeah, it has its place on bigger racks. And I don't know, smaller stuff, supermarket stuff, I don't see the payback on parallel compression. Maybe at the like Texas border, maybe.
Yeah.
But in this instance, I don't think you're going to see a whole lot of parallel compression, at least not for the time being. Now, let's go over the medium temp side of the hot gas defrost. So,
oh, wait, I got to bring up the other one. Hold on.
Yeah.
Hold, please. All right. There we go. I just want to make sure I didn't bring up another picture that someone's getting mad at me for. Stupid. All right.
So there's only a couple ways to do this. You have medium temp defrost using the ejector, or you have the zero zone Hill Phoenix style where they're taking critical hot gas and utilizing that. So let's go over that just real quick.
Mm-hmm.
So the transcritical style hot gas, and they're using a pressure reducing valve to feed a hot gas header.
Wait, this print or the other one?
I didn't have a print for that one, remember?
For the hot gas, for the full-on hot gas 140 bar system?
They're not 140 bar systems, remember? The zero zone style where we have the pressure reducing valve.
Oh, okay. All right, never mind.
I don't have any P&ID diagrams to that. So this style, I think that one was close.
That's what I mean. That's why I'm just going to bring this one up just for reference. You know what I mean? I know it's a little bit different. I couldn't find the zero zone. I looked on their website for like.
You don't have it.
I saw that.
So in this style, guys, we're utilizing the transcritical hot gas line, meaning post oil separator, just like they show on here. You got the oil separator, then there's a key in there, and we're going to a hot gas header, just like you would on a standard HFO or HFC rack. You're going to go to a hot gas header, then you're going to have a pressure reducing valve immediately afterwards. Now, this pressure reducing valve is an outlet pressure regulator. All it cares about is the outlet pressure of the hot gas header. So meaning the hot gas side going out to the systems. Now,
hold on, that would be, hold on. Well, if it's anything like this one, it'd be an inlet pressure regulator, because if it was an outlet pressure regulator, then it would be regulating this.
No, it's on the transcritical side.
Oh, okay. All right. So
Yeah.
this is different. Okay.
Yes. This is utilizing a low temp again. So this is on the transcritical side. So on your transcritical side of leaving the oil separator, you're going to be teed into a header going to a hot gas line. Now you're going to have a pressure reducing valve on there. That pressure reducing valve, all it cares about is that outlet header pressure. So it's trying to maintain that outlet header pressure anywhere from 550 pounds to 650 pounds. I've seen it anywhere in between there. It depends on the store setup and the set points from the manufacturer. Most of the time, I've seen it like 550 to 565. So they're trying to maintain like 40 pounds above flash tank. So say the flash tank's 500 to 515, they're trying to maintain 45 to 50 pounds above the flash tank pressure because they're going back into the flash tank. So again, just like the other system, you need to have that pressure difference between whatever you're flowing back towards. So they're flowing back into the flash tank. So you're going from the transcritical side. So you may be 1,200 pounds. Then you're reducing down to 550 to 600 pounds. And then that is giving you your pressure difference between the flash tank now. So now you have the flash tank running at 500 pounds. You're going back to that. So you got to be 50, 60 pounds above that flash tank pressure. So that outlet pressure regulator, generally, I've never seen a mechanical one. They've all been electronically driven. So either microthermal, CPC, Danfoss, they're all controlling this pressure regulator off of a set point. So they have a fixed set point in there, and it's constantly moving and opening and closing this regulator to keep that header pressure up. Now, the benefit to this is in the summertime, you get smoking hot gas going to this. Even though you're reducing the pressure, you still may have 200, 250 degree hot gas coming off those compressors. You do a quick defrost, like minutes. You get all that latent heat exchange, and then you get all that sensible heat exchange on there. So you're sending all that hot gas down there. Now, the issue is that pressure reducing valve. If it loses its place, if it doesn't have enough differential, if it has too much differential, it's going to blow reliefs. So you want to make sure that that valve is controlling very tightly. So that valve needs to be tuned in and actuating very tightly. And you don't want a big opening percentage on there, because if it opens too much, it's going to hunt and it's going to pop the reliefs. Now, that is setting your flow through the coils. I have seen in this instance, though, we've seen a lot of check valves stick in this style system, utilizing like cheaper check valves, and it's random. Like you'll get there and the rack will just flood out, and then you'll start it back up and everything's fine. And you'll run everything through defrost, it'll be fine. And then maybe 4 or 5 defrosts later, it'll stick again. And it'll wipe the rack out again. Because when it goes to start back up for normal refrigeration and we bring on the liquid line, it's just sending it right around the coil through the check valve right into the suction. Brett, you're muted again.
I just said interesting. I'm looking for something.
With this style system, the biggest issues I've seen is sticking check valves. And there was some Band-Aids in the beginning. Manufacturers were putting solenoid coils on the inlet to the valves, and if there was a low superheat situation on that circuit, it was shutting down the solenoid coil, and then it would restart and it would stop. Once there was no differential between the suction and liquid, once that liquid or that differential reset, the check valve would generally reset. And this was hiding the check valve sticking issue. The real issue was the check valves, not that it was flooding back post defrost. It was the check valves were sticking. Changing out all the check valves ended up solving this. Now, the benefit to this is it works for both low temp and medium temp without any additional components. You don't need ejectors. You don't need any extra heat exchangers. It's just one valve doing the pressure reducing, allowing it to have enough flow, and you're going to flow backwards through the coils like a standard defrost. You're going down the suction, you're coming back on the liquid line, and you're dumping it back into a header that's going to dump into the flash tank. Now, and then that liquid is going to be redistributed through the rest of the store. Now, one thing is you want to keep an eye on your term temps, because if you start hitting high term temps, you don't want to be pushing hot vapor back into the flash tank, because now you're putting load on the flash tank and you're taking away any subcooling that you may have in there because you're dumping hot gas in there. So you don't want to get your term temps too far above what your flash tank is. So if your flash tank's running like a 38, 40 degree, you don't want to have like 70 degree term temps. You're going to need to have like 55, 60 degree term temps, maybe 48. You don't want to have 70, 75 degree term temps, because you're just throwing all that hot gas in there. Now, you should see your frost pattern just like you would on a normal HFO or HFC rack. You should be able to watch everything go through. You should watch your term sensor on your dump line. You should watch it go up in temp immediately and then just start going down in temp as it starts condensing all that hot vapor through there as a liquid. And then as it starts to slowly climb up, your ice is melting off the coil. Just like you would troubleshoot a standard HFO or HFC, whether you have not enough flow or too much flow. If you're just staying hot all the time, like through the coil, if it's never like dipping back down, you're flowing too much. You have too much pressure differential.
The other thing is too, you'd probably do the same thing like in an HFO system, and you're running hot gas and you're not creating any more liquid and it's just straight gas coming back. That gas is going to flow through a hell of a lot faster than what it typically would, because there's no resistance of that liquid being created. Right? In turn, my assumption would be you'd probably also see a high closing percentage on your defrost differential valve.
It starts hunting like crazy.
That's what I'm saying. So it would stay constant, and then all of a sudden it's like trying to maintain that pressure because you're just sailing that hot gas right through that coil.
Correct. And that's why that's one of the things that's nice about having two different PID set points. Like microthermal has a winter and a summer set point. Mm-hmm. So in the summertime, you're going to defrost a lot faster because you have way more heat. Mm-hmm. That valve opening percentage needs to be way lower. And in the wintertime, that valve minimum opening percentage needs to be higher, because you're going to have more flow through there for longer in the wintertime.
Yeah.
But generally, this style is no different than troubleshooting an HFO or HFC system for hot gas. It runs the exact same, minus the fact that instead of a defrost differential valve, we have another defrost differential valve that's looking at outlet pressure only, not differential pressure. So it's setting its differential pressure just based off whatever the flash tank versus the defrost header would be.
Gotcha.
Now, the ejector style, we'll go over that with the medium temp.
Yeah, hold on one second. Bringing it up now. Right there. And add to the stage. There we go.
So this style, guys, with the ejectors. So what they're doing is they're taking vapor off the top of the flash tank, and they are running it through a reheat heat exchanger. Now, this reheat heat exchanger is what's heating that vapor off the top of the flash tank. So your flash tank vapor may be 34 degrees, so your set point may be 33 to 34 saturated on the flash tank. You may have 10 to 15 degree vapor superheat coming off of there. So you may be 40, maybe 42 on there coming off of the vapor off the top of that flash tank. Now, when you are going to get a very poor defrost with 40, 42 degree vapor. It would do it, but you need to add some heat to that. So what they're doing is they're running it through a heat exchanger coming off of transcritical compressors. And what they're doing is they're forcing transcritical gas through there, and they're reheating that vapor up. So you may have 180 degree, 220 to 250 in the summertime, depending on how high the pressures are, vapor going into there. And what they're doing is they're going different directions. So you have gas coming off the top of the flash tank going one way, and you have that hot gas discharge going the other way, and they're heating them up. So you're heating up that flash tank, and at the same time, you're actually cooling and de-superheating the medium temp compressors. So you're taking some of that discharge gas that would have been going to the flash tank, or I'm sorry, to the gas cooler, and you're de-superheating it. So now you're doing two things when you're doing this. You're taking some load off of the gas cooler. So now it's going to be doing a little bit more cooling, and you're going to get a little bit more liquid out of there. And at the same time, you're superheating that vapor coming off the top of the flash tank. And now you're taking that vapor and you're taking it to a header, and you're going down the medium temp liquid. You're going through the expansion valve, because this is an inverse flow system. You're going through the expansion valve. So you manually open that wide open. The program does it. When it goes into defrost, it opens that valve wide open, and it's going to flow backwards through there. And then you're going to go back to a header. You have a return header that's going to go through this ejector. Now, this ejector, think of it like a compressor almost. So it's sucking on that header. So it's creating the differential for you between your flash tank inlet pressure and the ejector outlet pressure. So your ejector outlet pressure is going to be, your lift line is what they would call it. So you want to have generally 15 to 20 PSI from the lift line header, meaning the hot gas return header, to your flash tank. You need that 15 to 20 PSI to have enough flow in order to keep that gas rolling through that heat exchanger to get superheated, then drop back to your defrost header, then sent out to the systems to get everything defrosted, then to come back as a liquid to drop back into the flash tank through the ejector. You're muted.
Because I keep coughing, I'm trying to cover up coughing. Is this because this is the valve that normally opens up to let the refrigerant go through the gas cooler? So is this the one that's going to regulate to make more flow go through the PHE, this heat exchanger, to
Correct.
Increase the temperature? And this valve right here, inlet or outlet regulator?
So neither. It's just a BLEMO valve.
It just closes fully, or?
It does both. So I've seen it two ways of them doing it. I've seen it where they close that valve and just force gas through the heat exchanger.
Mm-hmm.
And then, because you see the other side of the heat exchanger ties back into the condenser line.
Oh, okay.
So I've seen it where they just close it, and I've seen it where they modulate it. So they modulate it, and then say if it's 75%, it's forcing 75% of the flow through the gas cooler immediately, and 25% is going through that heat exchanger. They're trying to maintain that outlet of that heat exchanger 125 to 150 degrees, whatever they can get it to. So that line, you have enough vapor temperature to defrost those coils. Now, this is like think of it like hybrid cool gas, because you're taking vapor off the top of the flash tank, just like you would be on the receiver. So it's more of a latent defrost system with a little bit of heat added.
So does this ejector look almost like, remember they came on a lot of the Costco racks? It looked like a big old T and it was painted red, orange, and
Yes.
blue. Is
Yes.
that exactly what that is, or is it just something different?
Basically the same. So what it looks like is it's a cylinder.
Mm-hmm.
It has a BLEMO valve attached to it
Mm-hmm.
to modulate. So you have the ejector valve where it says ejector open on the line right there. There's a BLEMO valve on there that modulates the ejector that creates a pressure differential.
It might be that same damn
It basically is the same thing. It's an orifice inside of an orifice, or it's a tube inside of an orifice, and it's basically the same thing.
Gotcha.
So those hill racks did the same exact thing. That ejector works just the same principle.
Gotcha.
Now that is how they're making a differential. Now they modulate that BLEMO valve to make that differential, because obviously if this is all dependent on drop leg pressure. So if your drop leg pressure is really high, meaning like you're running transcritical and you have 1,300 pounds of pressure, you're going to have a ton of ejector flow. An ejector is going to do a lot of work. Now, if you're 700, 650, something in that range, your ejector is going to become way less efficient because now you have less flow to drive the ejector.
Do they have anything in the program where it tells it to boost the pressure up, like it's running minimum saturated condensed temperature, or is it runs at whatever it was running at before?
So I've seen it both ways. I've seen it where they've used the 326 heat reclaim.
Yeah, the input. There's an input in there. iPro has that too, where you can put an input in there and basically tell if it's running heat reclaim or not, and then it has a secondary set point, right?
Correct. And like, I hate doing that. Like, I hate running the racks transcritical. From everything that I've messed around with and seen, like, it doesn't pay. The payoff is not there. These things run high enough discharge temps all summer long and all winter long, where we shouldn't need to run them transcritical in the middle of winter time to get more heat off them. Like, you get plenty of heat.
I wonder if, like, instead of having because I know it's done. I've heard of places that I'm sure out in Arizona there are places, but I've heard where they run a chiller, and the chiller then becomes the gas cooler, just so they can run a heat exchanger at a lower temperature, so it does not hit transcritical. So you don't, obviously we've talked about this, we've probably beaten this horse, to death. But the reason why we have so many medium temp transcritical compressors is to take that excess flow from the flash tank that's being created when we are in that super critical state. Right? So by lowering that all the time, we could probably minimize the amount of compressors that we have, or minimize the amount of horsepower that we would need on the medium temp transcritical side. So we wouldn't have to waste so much energy. But I don't know. It's one of those rob Peter to pay Paul things. Like, is it going to be the same amount of capacity that you rip off of here? Is that the capacity that you're going to need in order to do that with the line, keeping it under transcritical pressures?
Let's think about it like this, like what you just said. If you had a water cooled rack and you run a water cooled gas, obviously you're going to lose some efficiency with a water cooled condenser. It's just, you have two different mediums. You're going to lose some efficiency there.
Yeah, it's
a lot more efficient to run a 16 SEER, 20 SEER HVAC compressor than it is to run a 5-6 SEER refrigeration compressor.
True.
And then you're already doing comfort cooling. And then I 100% the most missed thing there is heat reclaim with transcritical CO2. That is I think the biggest abatement method to keeping it transcritical. Like, I've watched Aldi racks in the middle, 95 degrees out, with a 55 degree drop leg coming off of the heat reclaim.
Wow. That makes sense. I mean, like you said, it's probably a cost thing, because you gotta get rid of it somewhere. So, like, for a remodel store, it might be a little bit harder, because then you got to change some of the attributes of the HVAC system to fully get your heat reclaim used for the whole facility. I've seen a lot, like, where you'll have a packaged X customer that has, it's transcritical, but it also has water heat reclaim, and it also has air heat reclaim. But the only difference is that, what I've seen is they usually put a heat exchanger in there, and the glycol basically transfers the energy. I don't know the principle on that because, like you said, it'd probably be more efficient just to run the CO2 directly into the heat exchanger tanks or run the CO2 directly into the air heat reclaim. But one, it would add increased charge, which isn't really a big deal with CO2. But then you also run the risk of, hey, we have a leak in the air side of the CO2, and it's essentially dumping CO2 directly into the living space.
It's no different than having a leak in a case, though, at that point. I don't get the glycol thing, but I don't like it. A lot of times they're inoperable because of leaks or other things. And
Shaft seals, man, they leak on those red
yeah,
parts.
and then you're just losing efficiency at that point. You have a pump now, you have glycol, you have all this other stuff. You have a primary, secondary pump. It's overcomplicated. Just use air heat reclaim. Air heat reclaim, you get so much more benefit out of it than that. And then running it transcritical just blows my mind. But again, back to the ejector troubleshooting. If your discharge temps are too low, you're going to have problems with the system. Meaning, so if you're flooding back on your medium temp, you're going to reduce your hot gas capacity because you're not going to have that ability to reheat. I'm still going to get some out of there, but if you're flooding back in your medium temp, you're going to reduce that capacity. Now, if your drop leg pressures are too low during defrost, meaning if it's like minus 20 outside and you could barely maintain a 600-pound drop leg pressure, you're probably not going to have good ejector flow. Now, in this particular system, they're actually flip-flopping back to, since this is medium temp, they're flip-flopping back and forth to off time. So the way that these Carnot systems work, at least in the Costco's, they use the dual temp input. So when the ejector is good to run, all the cases switch to being able to run a secondary set point of hot gas. Now, when it's not calling for it to run defrost, or none of them are okay to run, meaning like the ejector, there's something wrong with the ejector, the ejector doesn't see a pressure it likes, then they all are off time defrost.
Is there a set point as far as discharge pressure on the gas cooler that's going to say, hey, this is way too low, I don't want you to run right now?
Yes, I believe it's like anywhere from 600 to 800 pounds. I've seen multiple stores be different.
Really?
So what they're doing is they have an ejector okay to run, and as long as the ejector is okay to run and everything's good with it, when a circuit calls for defrost, it flips in their block logic, it flips the dual temp switches to all the cases. So all the cases go into dual temp mode, or whatever's on that rack associated with that goes into dual temp mode. Now, what that does is it changes the EEV and the fan cut settings. So the fans may go from turning off in defrost to not turning off in defrost. So if it's in ejector mode and a circuit calls for defrost, it's in the dual temp mode now, and meaning it's going to have a fan stop. As soon as it goes into defrost, the fans are going to shut off. The EEV is going to go to 100%. Okay. Then it's going to go through defrost. It's going to start defrosting, and then it's going to go through post defrost, meaning it's going to go through drip time. And then when it switches back to refrigeration, the EEV is going to open normally, and then it's going to cool the coil down. It's going to get to its fan cut in, meaning if it's like 26 degrees, the fans are going to come back on. Now, if it's not okay for it to go into ejector defrost, say there's an issue with the ejector, the pressure's too low, the heat exchanger is not functioning properly, we're not getting that temp, we go to off-time defrost. So now we go to an off-time defrost. So your fans will stay on, your EEV will close during defrost now instead of open, and your defrost termination will just be whatever it's programmed to, and it'll go through an off-time defrost. Now, this is the caveat with it. Your defrost time needs to be set for off-time defrost. So if it's a case and it needs 45 minutes, it's going to be 45 minutes. If it's running ejector defrost, it's going to run through its minimum defrost time. So if it's 45 minutes, say it's maybe the minimum's 15 or 20 minutes.
Mm-hmm.
And then after that, it's going to term out, whatever the termination is.
Gotcha.
So when the ejector is functioning and everything is good with it, it will run like a normal hot gas defrost, fan shut off, everything like that. When it's not functioning, it's off time defrost.
So even though it's a medium temp, you still need to have the fans hooked up to the output for the fans, because sometimes it might shut off the fans during defrost, sometimes it might not.
Correct. Now, generally with cases, they were running them all the time.
Yeah.
We were utilizing the fan shut off on the meat cases because it was making the product too hot, too fast. It was turning. But like deli cases, I generally left the fans on, and it helped it defrost. Just any open case, generally the fans stay on.
Where the hell is this spec? This is my question, because I know we've beat this conversation to death too, but like, this would be a lot easier if people would just give us the sequence of operation. I mean, you're very familiar with this because you've done a crap ton of programming with these.
I just finished because I just got 4 of these racks and none of this reheat was done. So I had to finish it all.
That's what I mean. Like, if more manufacturers would give the sequence of operation for stuff. That's the thing. Like, I can fix anything as long as you tell me how it's supposed to work. If I don't know how it's supposed to work, how is in a generalized fashion, how is anyone supposed to fix any of this if they don't really understand how it's supposed to be running? If it's what's normal.
You've seen some of the programming for this stuff. I feel like it's overly complicated there's simpler ways to do things.
Yeah. But I just mean like any manufacturer. I'm not speaking about one generalized manufacturer. I'm talking about any of them having that sequence of operation. I mean, look at all the stuff that Hill Phoenix puts out as far as their cases and stuff. It tells you exactly how much drip time you're supposed to have, how fast the fans are going to be rolling, how much airflow. Like, that makes diagnosing that stuff a heck of a lot easier than some of these other manufacturers that, it's a secret, we can't tell you.
I honestly think some of it's like copyright laws.
I got you a tinfoil hat for Christmas.
I did stop it. Like, you know damn well, like they're just as petty as we are. You got engineer A suing engineer B because something looked like something they did. But in a nutshell, that's hot gas defrost troubleshooting.
Learned some stuff today. That's it.
Yep, that's it. My eyes are toast from looking at the screen.
All right, guys. I guess we'll see you next time.